it just has an expire time that says when this timer should fire. And then it has a callback and an opaque pointer that is passed to that callback. And so once a second, the QEMU timer fires and calls this RTC update function on that RTC state struct. But if we free it, it frees the RTC state structure, but it doesn't free or unregister actually either of the timers it used. I've only shown the one that's relevant for this exploit. And so we're left with dangling pointers. That opaque pointer there is actually used as a pointer to the RTC state, and so we have a dangling pointer to a free object. And so within a second later, at the next second tick, we call this RTC update second function on a freed object. And we have a classic use after free bug here. As those of you who are exploit developers probably know, that's almost the most beautiful case you could hope for today for an exploitable bug is a use after free like that. And just to show how easy this is to reproduce, that's the reproducer. Compile that program, run it as root in a Linux machine on a vulnerable version of KVM, and KVM will segfault. And you know, all this does is IOPL just gets privileges to be able to write out IO ports, and you write a single value to a single IO port, and boom. And in fact, this bug was found by a fuzzer that just literally wrote random values out random IO ports, and eventually it stumbled on this value, and I get a signal 11. And I went and debugged it and wrote the stalk. All right. So that's the bug. So we have this beautiful use after free. But so what does it take to, in the KVM environment, go from a use after free like this to a working exploit? We'll talk about this process in 3 stages. You know, first off, how do we go from this use after free to controlling the instruction pointer? How do we get KVM to jump to some address that we specify? And then once we have that, how do we leverage that into executing arbitrary shellcode inside the guest? And then once we have, and then I will have talked about those two, assuming that I can guess addresses in the QEMU KVM process, i.e. that there's no address space randomization in the process, that I can predict addresses. And then we'll talk a little bit about what we have to do to get rid of that assumption, to work on a process with a randomized address space like KVM is going to be in the wild on any real deployment. So for getting RIP control, the high level to do is sort of fairly straightforward if you look at how the code works, is we're going to need to create a fake QEMU timer object that we control and inject that at a known address. Then we'll trigger the eject, we'll dump the ISA bridge, and then we will force an allocation into the space previously occupied by the RTC state structure that points that second timer field at our timer. Then on the next second boundary, RTC update second will run on our fake RTC state, and it will reschedule the second timer to run 1 second later. But we've hijacked that pointer to point at our timer, and so 1 second later, our timer will run, which includes our callback method that it will jump into, and it will jump to code that we control. So there's 3 steps here. I've already shown you how to do number 2, how to eject the ISA bridge and sort of actually trigger the vulnerability, which leaves 2 things left to talk about. 1, how do we construct fake devices in QEMU KVM's address, fake structures in QEMU KVM's address space? How do we get objects that A, appear in that address space somewhere so that we can write pointers to them, and B, appear at a known address or find out that address so that we can predict that address and write that second timer pointer to point at our thing. So this is one case where exploiting a virtual machine is actually sort of in some ways has a unique advantage over many other types of exploits, is that process turns out to be incredibly simple. The way that QEMU KVM handles the emulated RAM for the guest is that it's just a big mmap region in QEMU KVM's address space. That is the physical RAM of the guest. So there is no injection portion like I talked about here actually at all. We just literally allocate an object however the hell we want, statically, mmap it, allocate it on the stack, whatever we feel like. Find the physical address of that find the physical address in the guest, which we can do in a couple of ways. You know, if we can do in kernel mode by walking the page tables explicitly, or the kernel actually, it turns out, exports a proc file that will just give us this information. But, you know, clearly we can find that from the guest. And then we just add that to the base address of the mmap in the host process, and we've found that object. For now, we're going to assume that we know the base address of that mmap, because this base address is predictable, assuming no ASLR. And again, we'll talk about how to get by that assumption later. So that's step one, is injecting data at a controlled address, actually totally easy when you're attacking a virtual machine. And this is true, I believe, in basically actually all current virtual machines do this or something similar. And so this is not totally unique to KVM, although this is the first exploit I'm aware of that's talked about this technique. Second technique is forcing allocations inside the QEMU KVM process. We need to get QEMU KVM to do a malloc and then populate it with data that we control of an appropriate size that it will, with high probability, get allocated into the space that the struct RTC state used to occupy. To do that, I'm going to use a feature of the QEMU KVM network stack that I'll talk about. QEMU KVM inherits from QEMU a user mode networking stack that implements an entire virtual LAN inside the QEMU KVM process. This is used as a way of allowing you to get network access to the guest without having to mess around with bridge devices and TUN-tap devices or other such madness on the host, and also without requiring privilege on the part of the QEMU KVM process. It's the default networking setup, so it's a reasonable thing to attack, although in production environments it's probably more common that we'll see bridge networks or something else, and so we'd have to modify this step there. But the same fundamental principles of most of the attack would apply. So this virtual network stack, emulates a DHCP server, a DNS server, and gateway NAT all plugged into this virtual LAN. And the way that this virtual LAN handles packet delivery is that normally packets are handled synchronously. When you inject a packet onto the virtual LAN, it just looks up the recipient and calls their deliver packet callback method synchronously. And so there's no buffering, no queuing. But in order to prevent recursion, if a virtual device or virtual host's deliver mechanism then injects a second packet in response to the first packet, that packet is queued using malloc with a small header appended, and then delivered later once we return to the main run loop. So if we can find a device on the virtual LAN that responds to packets from the user by synchronously generating a second packet whose contents are all or almost all controlled by the contents of the first packet, then that will generate a malloc with controlled contents. Can anyone think of a network service that has that property? Ping, ICMP ping echo packets. So the way we're actually going to force allocations inside the guest is by pinging the virtual gateway. And it will reflect the ICMP packets back at us with the payload of length we control and contents we control, which will force mallocs and let us exploit this use after free. And so now, putting the pieces together, we allocate a fake QEMU timer in our address space with a callback method pointed at whatever address we want KVM to jump to. We'll calculate its address in the host using the arithmetic I showed earlier. We'll do that eject dance, and then we'll ping the emulated gateway as fast as we can with ICMP packets that have pointers to our fake timer in the host. And with extremely high probability, basically one of those will end up allocated into the space previously occupied by the RTC state and will win. We have the ability to get the QEMU to jump to an address we control. All right. So That's part one. We have RIP control. We can get QEMU to jump to any address we want. But we still have to deal with non-executable pages or an injecting shellcode somehow. We're not quite there yet. So what are our options to do next? Well, we'll start with the classics. We can set EIP equals 41414141 AAAAA and declare that that clearly demonstrates it's possible and, we're done. That's boring. I could disable NX, non-executable pages, in my BIOS or in my kernel and, just blat shellcode wherever the hell I want and jump to it. That's also boring. Getting more interesting, we could use a technique called return-oriented programming to chain together bits of QEMU's own code to do the standard mmap or mprotect to allocate executable shellcode and then jump into the shellcode that way. This is a standard technique used in most exploits these days. It would be a perfectly fine strategy here, but I have a slightly different strategy that I happen to like, that I stumbled upon here, that I think has some cleaner properties and was easier to develop than doing a ROP payload. And so we'll talk about that. So let's take another look at that QEMU timer structure that we're faking. So we focused on the callback and opaque members before, but now let's look at this expire time and this next pointer. And so the way that these timers are implemented is they're stored in a sorted linked list threaded through by that next pointer. And every time the QEMU main loop wakes up, it runs these timers, which just walks these timers by this linked list, following that next pointer, as long as that expire time is before the current time. And so we control that next pointer because we control this entire timer. So what we can do is construct multiple timers and chain them together by that next pointer so that we can cause QEMU KVM to execute multiple functions in a row and perform sort of limited strings of computation in the host rather than just doing one jump. And we're going to point these functions at existing functions inside the host that we're going to string together in an unexpected way. So this is sort of halfway between traditional return to libc attacks and ROP attacks, with a slightly unorthodox method of doing the dispatching. So now one feature we notice here is that we have a large number of one argument function calls. We want to do more argument function calls. So to do that, we're going to dive a little bit into a detail of the AMD64 calling convention, how it works. So on AMD64, which I'm assuming, we pass arguments to functions in registers, starting with RDI, RSI, RDX, etc. So RDX is the first argument. That's going to get the opaque member of our fake timers. RSI we don't directly control. However, every compiled version of QEMU run timers that I've encountered leaves RSI untouched. It doesn't clobber RSI. So suppose that we found a function that looked like this hypothetical set RSI function. It sets the RSI register based on the RDI register, which is the first argument register. So if we go back to our chain of function calls, we set F1 to set RSI, and we pass it some argument. And so then we're going to populate RSI with that first argument, that argument to the first timer. RSI is going to get populated with that. And then we call the second function. We now control both arguments. So we can get to two arguments this way. The same trick doesn't work with RDX, the third argument register, because QEMU run timers does clobber that. And so we can't count on it being preserved across different timer calls. So we'll talk about what we do there in a second. First, this function happens to be the set RSI gadget that I chose. What this actually does in QEMU is relatively unimportant, but the detail is it takes a value as its first argument, and then it calls a function with that value as the second argument, which means that it moves it into RSI. And so as long as we choose a value of adder that makes IO port write a no-op or mostly harmless operation, this has the effect of populating RSI from RDI. So that's that. So now, to get to a 3